Next one has a cube root. So whenever we have an odd root, this, whatever makes that equal to 0, will not be differentiable. Okay? Square root, fourth root are different. So going back to the first page, sorry, I'm just going to scroll back so you can see it. Anytime you have an odd root, you get a vertical tangent. Okay? That's where the graph goes from here, right? And then here. So you end up with this vertical tangent right where it switches direction. So if you look, basically you look at the transformation. So in this case, right, we have x minus 2. So if you set that equal to 0, you get x equals 2. That's where it's not differentiable. Okay, so it's not differentiable here. So it's everywhere else. So we'd have negative infinity to 2, and then 2 to infinity. So you have to look at what the situation is. If it's a discontinuity, then you just look at, for example, the rational functions, you just look at where the denominator would be 0. If you have a cube root or a fifth root, you look at where the transformation, like where it would switch, and that's where it's not differentiable. What if you had a cusp? Same thing. I mean, basically if it was x to the, like we had one on the previous page, it was x to the 4/5. It would just be x equals 0. If there was a transformation, then we would take that into consideration. Okay, this is, we really don't discuss this too much in this class, but I put it in here. Intermediate value theorem for derivatives. It just means, let's say you have a point here. Let's say here's A, and here's B. Or actually, this is B. So this would be f of B and f of A. If you have this slope here and the slope here, if it's differentiable, then let's say, what's your, approximate the slope there. Maybe the slope is equal to, well, what's it, like look at this right here. What, if you had to estimate the slope of that little line segment, maybe 1, m equals 1? Yeah. And right here, what would be, m is equal to 0? So that means this has to take on, yeah. So I have to have all values. The slope has to take on all values between 0 and 1. That's all it says. So, for example, could I say, is there a place where the slope is equal to 1/2? Yes. Is there a place where the slope is equal to -1? Not necessarily. It has to stay between the two slope values that I have indicated here. Is there a place where the slope is 3/4? Yes. Yes. Is there a slope of 1/4? Yes. Okay, so that's all the intermediate value. It has to take on all the slopes values in between there. This one?
Yeah.
Uh-huh. Oh, okay. All right.
So do we put everything with 1 and 0? Like, 0.
Okay, we started, so number 5 is very similar to that problem that we just did in the notes. So number 5 is just a line segment. Okay? So if you have just a line segment, where is it differentiable? It's going to be differentiable over its domain. So what is this? -3 to 2. Right? Yeah, -3 to 2. Right here. You see it in brackets? And then where is it continuous but not differentiable? There's none of them. Because remember, what did I say in the notes? I said you want to look for if it has a cusp, a corner, or a vertical tangent. It has none of those. And then same thing for part C, where is it neither continuous nor differentiable? well, it's continuous everywhere. So that's fine. The next one after that was number 7. Number 7, now where is it differentiable? From -3 to 0, parentheses, and then 0 to 3. Where is it continuous but not differentiable? Is there anywhere? Nowhere. And where is it not continuous? At x equals 0. Does that make sense? Okay, the next one goes to number 9. Okay, number 9. Okay, so where is it differentiable? This is, it looks like a corner or cusp. Either way, at 0, it's not differentiable. So it's going to go from -1 to 0, parentheses, and then parentheses 0 to 2. Okay, so the way they wrote it, they wrote all points in -1 to 2 except x equals 0.
That's how I did it.
I would prefer, I mean, just so you, I would prefer -1 to 0 and then 0 to 2 like that. I'm just, because the way that I ask you on the quiz or a test, I'll say the intervals. That's all. And then for B, where is it continuous but not differentiable? Right there where it looks like it's a corner or a cusp, so at x equals 0. But part C, it's continuous over the whole thing. So there are no points of discontinuity for part C. Next you had 11 to 16. You can graph them on your calculators. This is where, okay, so this is where you're able to graph it to see which one it is. And I said that you could, those would be calculated problems on a quiz or a test. So what would that look like? This is a piecewise function, right, for number 11? So how do you do tangent inverse? Just second tan. Make sure your calculator, and what's wrong?
No, I can't. With my calculator, it's very difficult to understand the corner and the calculator.
Yeah, so this one's tricky because you have to understand at tangent inverse, it can't be equal to 0, so even though you see it there, and then there's a point right here. So it's a discontinuity.
The calculator isn't really helpful in those sort of problems.
Yeah, the only way I would say this is as helpful is to do the table. But see how you have a y2? It's confusing. Yeah, because it has 2 separate ones there. How about number 13? Number 13, what happens in 13? Square root of x squared gives you an absolute value of x. So that's going to give you a corner. Here's an absolute value. Anytime you have an absolute value, that's a corner, automatically. Unless it's the absolute value of x over x, but then that makes it also rational. And then jumps to 31.
We're gonna have to do all of them.
Now it's 11 to 16 on the graphing calculator. Oh, did I skip some? Oh, I skipped the evens. Oh, you guys can see we did this one on our notes. Number 12 is from our notes. Cube root of x, that's a vertical tangent. The cube root of absolute value of x, when you graph that, you would get a cusp. There you go. You got the evens. I'm sorry, what, Matthew? I like interval notation for part A, but then for part B and C, it's just x values.